Hello everyone. In this video, I will explain what is pumping lemma for regular languages. The theorem is described as follows. Suppose there is a language L and it is a regular language. Then there is an integer n so that for any x that belongs to L, suppose there is a string x that is in the language L and the length of the string is greater than or equal to some integer n. There are three strings u, v and w so that x is made up of u, v and w. That is x is concatenation of u followed by v followed by w. With the condition, this is the first case, first rule. The second rule of the pumping lemma is that length of u and v has to be less than or equal to n. We can see the second case, length of u, v is less than or equal to n. Length of v has to be greater than 0 means it cannot be a null string. Length of v has to be at least one character long. For any m, take any integer m greater than or equal to 0 and we have the string u, v raised to the power m followed by w should belong to L. This is the pumping lemma. So what we have to do, we have to follow this. First of all, suppose there is a language L, we assume that there is a language L which is regular. Take some string x of length n or greater that belongs, and x should belong to the language L. Now divide the string into three parts u, v and w. Following these conditions, length of u, v together, that is length of u concatenated with v, should be less than or equal to n. That is, it has to be less than the string size, less than or equal to the string size. Length of v has to be greater than 0, it cannot be null. For any integer m greater than or equal to 0, u followed by v raised to the power m, w should belong to the language L. So what is the idea? In order to use the pumping lemma to show the language L is not regular, so note down this also. Pumping lemma is used to show that language is not regular. We must show that the language L fails to have the property described in the lemma. So for that, what we need to do, initially we start by assuming that the language is regular and we derive a contradiction to prove the language as non-regular. We will be doing this by some example in the following videos. Now, note down the second point. Pumping lemma is used as proof for non-regularity of any language. So what is pumping lemma is used for? It is used for proving the non-regularity of any language. If a language is regular, it always satisfies pumping lemma. Note down this point. If any language is regular, it always satisfies all the pumping lemma cases, what we have discussed above. Now we will see the small proof of pumping lemma. Let there be any finite automata M that is accepting the language L. Let n be the number of states of M. Let n be the number of states of M. Remember that since M is a DFA, n has to be some finite number because it has finite number of states. Assume any string x that belongs to the language L, means the language L has some string x and length of x is greater than or equal to n, means the length of string is either more than the number of state or equal to the number of state. Consider the path from start state to accepting state in M that corresponds to x. The length of this path is greater than or equal to n. Now consider any path from the start state to the accepting state in the machine M, that is DFA M, that corresponds to x. That is, the machine is now reading x, the characters of x, alphabets of x. X is some string in the language L, and that path is equal to length of x, which is, and we already know point number 2 says that length of that string is greater than or equal to n. Since M has at most n states, maximum of n state, we know that, and n is less than m, means the number of memory element is less than the number of characters or path in the while reading the string. some state must be visited. It means that some state must be visited twice or more in the first n steps of the path. Now see this example. We have a language equals to a raised to the power I, b raised to the power I for some I greater than equal to 0. We need to prove that language L is non-regular using pumping lemma. So for that, what we need to do, first of all, in step 1, assume that language L is regular. In step 2, take some x that belongs to L and length of x is greater than equal to some integer n. So we will take x as string number of a's followed by n number of a's followed by n number of b's. So x is equal to a raised to the power n, b raised to the power n. Now what we need to do, we need to divide x into three parts, u, v and w. I hope you all remember the rules for pumping lemma. See this? The rules for pumping lemma, we need to divide x into three parts, u, v and w. Length of u and v has to be less than or equal to n. Length of v has to be greater than 0, means we cannot take v as a null string. So we'll follow the rules here. We divide x into three parts, u, v and w. Take some u, as suppose I take it as a raised to the power n minus 1. And we know that v cannot be null. I take the string a. V is equal to a substring a. And w is v raised to the power n. So if we concatenate u, v and w, we will get x. We can clearly see that x is nothing else but a raised to the power n minus 1. Concatenated with a, I'll get a raised to the power n followed by bn. So now we have to check this distribution has to follow the restrictions on length of uv and length of v we cannot have null. So check this. We need to have length of u and v less than or equal to n. What is the length of u and v together? You can see that a raised to the power n minus 1, a raised to the power 1. So length is equal to n. So this condition is satisfied. Similarly, check for length of v. Length of v is 1, that is not equal to null. Therefore, this condition is also satisfied. Okay, fine. Now we'll check the fourth rule, that is take some integer m greater than equal to 0 and we have to perform this operation and check if the resulting string is in the language L or not. Start with, suppose if I take m is equal to 0 and I perform this operation, this becomes u, anything raised to the power 0 will give us a string null w, so uw. Now what is in u? U is a raised to the power n minus 1. What is in w? We have b raised to the power n. See the distribution we have taken earlier. U is a raised to the power n minus 1 and w is b raised to the power n. So we can clearly see that this resulting string where number of a is not equal to the number of b's. So therefore this is not in the language. So we have concluded with a contradiction, as we have assumed earlier that L is regular, but the resulting string we are getting here is not in the language L. So this leads to a contradiction. So therefore we say that L is not regular. We have proved using the pumping lemma that L is not regular. Now see this example. It says that L is equal to e raised to the power I for some I greater than equal to 0 and then 1b. So what we need to do, we have to prove that if this language is non-regular. So start with L is regular. Assume that language L is regular. We assume it as regular. The second thing is find any x that belongs to L and length of x is greater than equal to n. So I will write this as x is e raised to the power n followed by b. We can clearly see this pattern is in the language L and length of x is greater than equal to n. So what we need to do next, we divide x into three parts u, v and w, and we know the constraint length of uv has to be less than or equal to n, length of v has to be greater than 0 and uv raised to the power m w should belong to L. So now for any m greater than equal to 0, we can clearly see that we can divide this as a raised to the power n minus 1. Take v is equal to a and the remaining substring will be in w. Now see, check if the constraints are satisfied. U and v, length of u and v, see this and this together. This is a raised to the power n minus 1 followed by a. So length is n, which is less than or equal to n. Condition is satisfied. Similarly, length of v is greater than 0, so that this condition is also satisfied. Now we'll check for any m. Say start m is equal to 0. Check if u v raised to the power m w belongs to L or not. Here we have a raised to the power n minus 1. This is a raised to the power 0 followed by w b. A raised to the power n minus 1 b. See the string. The string says any number of a's followed by b is in the language. Yes, it is in the language. So a raised to the power n minus 1 belongs to the language L. Check for one more b, one more value of m. Suppose I take m is equal to 2. Put this, I'll get a n minus 1 a raised to the power 2 b. It becomes a raised to the power n plus 1 followed by a b. So it is also in the L and so on. For every value of m, we can clearly see for every value of m and so on, this resulting string, if you put this, it is in the language L. So for every value of m, I am getting a string which is in the language L. So we are not getting any contradiction. And if remember that we have assumed that L was regular and we are not getting any contradiction, it means that this language is not non-regular. It is a regular language. Therefore, we prove that we say that L is regular. Remember that using pumping lemma, we are proving the non-regularity of the language. Whenever I get any language which is we are not able to prove as non-regular, it means it was regular and we cannot prove it for non-regularity. So L is regular in this case. Hopefully this is clear to you, all of you. Now see this example where language L is equal to a raised to the power I, b raised to the power j for some integer I is greater than equal to 0 and j is greater than equal to 0. So first thing what you need to do, we need to assume that L is a regular language. Now second thing what we need to do, take some string X that belongs to L. The pattern the string has in L, take that pattern in X. We have any number of A's followed by any number of B's. So suppose if I take, and the length of X has to be greater than equal to some integer n. So I put this X as a raised to the power n followed by some b raised to the power say s for some integer s greater than equal to 0. Now divide x into three parts, u, v and w. We know the constant u, v has to be greater than or less than or equal to n, sorry. This has to be less than or equal to n, and length of y has to be greater than 0, and we'll check whether u, v raised to the power m, w belongs to L or not. So check this. U is, we'll divide this a raised to the power n into two parts, u and v. I'll take a raised to the power n minus 1 in u and a in v. W is b raised to the power s. Now we'll put this m, take m is equal to 0 and u, v raised to the power m, w. U is a raised to the power n minus 1, v raised to the power 0 and b raised to the power s. This will become null. So we have some string of this kind, a raised to the power some integer n minus 1 followed by b raised to the power s. This belongs to L. Similarly, if I take m is equal to 2, I'll get this u, v, 2, w. So this is a raised to the power n minus 1. This becomes a square and this is b raised to the power s. So this is a raised to the power n plus 2 minus 1 followed by b raised to the power s, that is a raised to the n plus 1 followed by b raised to the power. This is also in L. Now you can just check that for any value of m, the resulting string is in L. We are not getting any contradiction. And if we do not get any contradiction, it means our assumption is true and the language L is a regular language. So I say that L is regular. We could not find any single exception which is not in the language L by applying the pumping lemma. Remember, I have already told that earlier that pumping lemma rules is satisfied by any regular language. So we are not getting any contradiction. Whenever I take the language L, initially, if the language is regular, we could not get any contradiction. So we cannot prove for non-regularity of that language. So hence, therefore, this L is regular in this case. Let me take any other example. Suppose this is the language L is WW for any W that belongs to AB closure, AB whole clean closure. It means that the strings in L is of the form, suppose if we have any string AB, then it has to be followed by AB, AB, AB or BB, A, BBA. Such kind of string has to be there. So first thing what we have to do, assume L is regular. First thing, I'll assume L is regular. The second thing, take any string X of this form. Suppose I have AN, BN. So it will be followed by A and B. I take this. And we can clearly see that this W and this is also a W. So this string X is in L and length of X is greater than equal to N. Now the third thing what we need to do, divide X into three parts, U, V and W. Now suppose if I take X, U as A raised to the power N minus 1, V as A and W has all the remaining part of the string. Check if U and V is less than or equal to n. It is less than or equal to n. Length of v. Length of v is greater than 0. Yes, it is satisfied. Now I'll check the third case, that is, we'll check u v raised to the power m w belongs to L or not for any value of m. Take m is equal to 0 and put this u is a raised to the power n minus 1, e raised to the power 0 and followed by b raised to the power n, e raised to the power n, b raised to the power n. What I get? This becomes null. I get e raised to the power n minus 1 followed by b raised to the power n, e raised to the power n, b raised to the power n. You clearly see this string, the resulting string is not in the language. It is not WW. These two parts are clearly different. So this is not in the language L, and hence we have got a contradiction. So therefore, what we know that L is non-regular. If we get a contradiction on any value of m, we do not have to check for any other value of m, because here we started with m is equal to 0, and on m is equal to 0 only I am getting a contradiction, that is I am getting a string which is not in the language. So we can clearly say that the language L is non-regular language. Thank you for watching the video. Please do write your comments.